So P and G, our equations are pretty basic. So what we're doing for P and G is, so P and G equations apply to a solid of revolution. So it has to be a solid that's rotated about some axis. It doesn't apply to anything else. And so our surface area is the sum of theta r bar times L, and where we rotate the line. So you got the cross section of the shape, the lines, the perimeter of that shape. So the total length of those lines are the L's, and then you're rotating all of those L's about the rotation of the solid, which is usually 2 pi, but it may just be some other angle which you need to pay attention to. So the surface area, you're rotating the lines. For the volume, you're rotating the areas. And so your equation is the sum of theta times r bar times area. And so let me just show you some examples. So this is super common. So this is like a silo problem. So you basically have a quarter circle, which touches the z-axis, and then a rectangle that touches the z-axis. And so these are areas, and we're asked to find the volume and the surface area of this shape. And so, and they all rotate about the z-axis, and so it's a full 360 degrees, which is 2 pi, and you end up with a shape that looks like a silo, basically a cylinder with a hemispherical top. So what I like to do is I like to draw a picture of the area that I'm rotating. So I'm rotating a quarter circle and I'm rotating a rectangle. And so for the volume calculation, the area of a quarter circle is pi r squared divided by 4. And the r bar is 4r over 3 pi. And so 4 times 1.5 divided by 3.5 gives you r bar. That's for the quarter circle. For the rectangle, the area is easy. It's just 1.5 times 2, which is 3. The r bar, and again, the r bar is the distance from the axis of rotation to the centroid of the area. And so the r bar is half of the 1.5, which is 0.75. And of course, the area then is 1.5 times 2. So the volume is the sum of theta r bar times A, but the theta, said everything is rotated through 2 pi, we can bring the 2 pi out of the sum, and so I got 2 pi, and then r bar times area plus r bar times area, and the volume is 21.2 meters cubed. And so the volume is I'm rotating the areas through the angle. And it's this is in the centroids chapter because the r bars are centroids of the shapes, the distance from the centroid of the shape to the axis of rotation. We typically do it in this way where we're rotating each of the segment, the component areas. You could actually do this differently. You could take this composite area, find the total area, find the total centroid, and then you could just use the 1 r bar to the center of the composite area, and then you can use the total area. We never do it that way, but you could. You could do it that way. Questions on volume? Okay, for surface area, it's the same procedure, but now we're just rotating the lines. And so we have to use our line centroids and our line formulas. And this is where you have to be familiar with the line centroids. So a line, so the circumference of a full circle is 2 pi r. A half circle is pi r. A quarter circle is pi r over 2. So know your circumference formula. And so in this case, the length is pi times r divided by 2. So pi times 1.5 divided by 2. R bar, so that's the length. R bar for a line is 2r over pi. And so 2 times 1.5 over 2 is 3 over pi in this particular example. Again, don't confuse the r bar for a line with the r bar for an area. Know the difference. A lot of students mess those up. And so that's the line. The vertical line, his length is 2. His r bar is just 1.5. And again, I like to draw these shapes and I like to draw the centroid so I know what I'm doing. And then the other thing you got to be careful about on some of these problems, like the surface area problem, is sometimes the problem will say neglect the bottom. Sometimes the problem will say include the bottom. So read the problem carefully. In this case, I included the bottom of the silo. But if you're painting it or putting siding on the silo, you don't need the bottom area. You know, the bottom is you're going to put in concrete or something. So just read the problem carefully as to whether you need the bottom or not. In this case, I included it. So the area of rotation is 2 pi. So you got 2 pi, and then get r bar times length, r bar times length, r bar times length of the 3 pieces. And then you get the total area. Questions on that? Does that make sense? And this is a very common problem. Very common problem. Almost every other exam will have, or final will have this problem on it, or something like it. But this is a shape that touches the y-axis. You can actually have a shape that's hollow. And so you can have a shape like this guy that's got a hole in it, and you're basically rotating a triangle and a rectangle. It's still 360 or 2 pi, but now there's a hole in the middle. So now when you're looking for your r bars, you're taking the radius of the hole, which is 1.5, plus the distance from this left edge to the centroid, okay? We'll work through this, but this is another case where your shape doesn't touch the axis. And so for the volume, we're going to rotate a triangle and a rectangle. And so the triangle, the area is 1/2 of base times height. So the base is 0.9 and the height is 1.2, and that's the area. The r bar is this 1.5 plus 1/3 of 0.9, which is 0.3. So 1.5 plus 0.3 is 1.8 for the triangle. For the rectangle, his area is 0.9 times 1.5, which is 1.35. And his r bar is 1.5 plus half of 0.9, which is 0.45. So it's 1.95 from the axis of rotation to the centroid of the rectangle. And finally, the volume is 2 pi times the sum of r bar times the areas, and you get the volume. Questions on that? So pay attention. Is the axis of rotation touch my area, or is there some distance between the axis and my area? Let's look at surface area. So surface area, so all of these are just straight lines. And so that, in that sense, it's easy. But you've got this like diagonal line, and so there's 0.9 this way, and it's like 1.2 this way. And so the length is, from the Pythagorean theorem, is 0.9 squared plus 1.2 squared is 1. So that length is 1.5. This length here is 2.7. This length here is 1.5. And this length here is 0.9. This inner radius is 1.5. This outer distance is 2.4. The midpoint between these two guys, I guess this is 0.9 wide. So 1.5 plus 0.9 over 2. So 0.9 over 2 is 0.45. So 1.5 plus 0.45 is 1.95. And so our area is the sum of is the 2 pi. And then this r bar times this length, this r bar times that length, this r bar times that length, and this r bar times that length. And then you get the surface area. Questions on that? You're rotating lines. Does that clarify P&G? Because all of you at the beginning said P&G is still kind of fuzzy. Does that make sense? Let's go to some tests. So those are the 3 topics. Let's go to our tests and look at those. See what we've got. These are exam problems. Oh, here we go. Let me show you this. So this is a fun, so the P&G theorems are actually pretty cool, and they make perfect sense. And you get a complex shape like a donut. It's like, well, what's the surface area of the donut? What's the volume of a donut? You go like, man, how would you integrate for that? That's a hard problem to solve. But if you think of a donut, that's got like a 4 centimeter early inner radius, and then a 2 centimeter radius of the main body of the donut. You say, well, the volume is 2 pi, which is the theta. R bar is the inner radius, which is 4, plus 2, which is 6. And then the area is just pi r squared of this circle, which is pi times r squared. And so 2 pi, 4 plus 2, pi r squared, and you get the volume is 48 pi squared. Pretty straightforward. The surface area, same formula, summation theta r bar L. So now the L for a circle, again, is 2 pi r. So 2 pi times 2. The r bar is 4 plus 2, which is 6. And then the angle, which is 2 pi. What's funny is for these particular numbers, you actually end up with the same number. The volume is 48 pi squared centimeters cubed. The area is 48 pi squared centimeters squared. In fact, when I did that, I'm going like, wait a minute, no way. It actually works out that you get the same number. Now, if you change this R and this R, they're not the same. So I actually worked 2 more cases. I'm going, what does that do? And so for a tighter radius, the area is actually larger than the volume. For a larger radius, the volume gets larger than the area. But for that particular combination with those particular numbers, you actually get the same number for the surface area. The units are different, because in one, the units are centimeters squared, and the other one is they're centimeters cubed, but you end up with the same number. And so but this is a neat application of donut shape. And I think that several years ago, we put a donut on an exam, and a bunch of people missed it. They're like, how do you do a donut? But if you understand P&G, it's actually really easy. Okay, wouldn't you agree? So that's a really easy example. Exam review. So here's an exam review. And so this first problem, this is typical. They give you 2 different functions, and they say choose a horizontal element. So you're not picking; they're telling you. Like, you choose a horizontal. So because they're telling you, you have to be able to set up a horizontal element or a vertical element. They don't usually do double integrals, which I don't know why, but you have to understand how to set up a vertical or horizontal. So they say a horizontal element. You're looking for x bar, and so what's the correct dA? So not even the whole integral. They're just looking for dA. And so the thickness for the horizontal element, the thickness is dy. And then you get x right, I call this x right and x left. And so x right is this y to the 2/3, and x left is y to the 1.5. And so the dA is x right minus x left times the thickness, which is dy. And that's the answer. So all they asked for was dA. That's not uncommon. They also might ask you for just the general setup for the numerator, which would be an x tilde times the dA. And so now you're just picking the one that's correct. Here's the silo problem. This one's looking for the surface area. It's 360. So also pay attention to the angle. Most of the examples we work is 360, but it's possible to have an angle that's 90 degrees or 270 or whatever. And so you have to convert that to radians. So whatever the angle is, multiply that times pi over 180 or 2 pi over 360, whatever it is. But this is 360, which is the full 2 pi. And in this case, they're looking for surface area. It says do not include the bottom. So pay attention. Is the bottom included or not? They say don't include it. And then this is the volume. And I guess that's for that shape. this picture doesn't agree with this. This picture, I think, is for down here. But these calculations are for this shape here, for the volume of this shape. And we just worked this problem. And I think this is just another problem that I made up, you know, of again. So this is a problem where the shape touches the axis and rotates around it. This is an example of the problem that's hollow in the middle. And so you have to take this R plus the R to these shapes to get the correct R on the rotation. Let's go to another practice exam. This is the 2022 exam. Keep in mind that these exams, that you got the 4 sections. Those 4 sections are internal forces, shear and bending, friction, and then centroids by integration, composite centroids, and P&G is the 4th section. But because of there's A, B, and C versions of the exams, they might not be in that order. And so what I like to do if I'm a student is I kind of know which section I know the best. And so what I personally would do is when I first opened the test, I would check to see what order the sections are in, and I would go to the ones that I was most confident in and kind of work to the ones I'm least confident in. You guys be the judge of that. So centroids. Okay. So this is a horizontal. This is a different problem, but it's the same. It's the same ask. It's a horizontal element. You're looking for x tilde. What is dA? And so the dA is the x right minus the x left, and it's dy thick. And it's easy to get the x. The x's in terms of y are really easy, and that's your dA. Here, it's just a ring, but you're spinning, read it carefully, you're rotating about the x-axis, not the y. And so you're spinning it this way, you're spinning it vertically. And so this is 3a, and so 3 times 2, so this is 6. And then this is A, and so this is 2. So this is 2, and this is 6. And so you're spinning it this direction. And so the volume, wait a minute. It doesn't make sense. There's just one area here in this picture. And so you got 2 pi. The distance is, okay, so this is the R bar. So the R bar is 6 plus 4R over 3 pi. And 4R over 3 pi ends up being 8 over 3 pi. So the 6 plus 8 over 3 pi, that is your R bar. And then the area is pi r squared over 4, and r is 2. And so pi times 2 squared over 4 is just pi. So pi is the area, this is your R bar, the rotation of the angle is 2 pi, and so this is the volume of this guy rotated about the x-axis. And then they're asking you about the surface area about the x-axis. And so now you're rotating 3 different lines. You're rotating this line, and this line. And the centroid, remember, is 2r over pi for this line. And this is 6, this is 7 to here. So that's the area. So that's a sample. Oh, and here's a composite area. So here's a composite area. And you can do this different ways. You can treat this as several rectangles and a triangle, but it's easier to treat it as a square that's 9 by 9, but then subtract off the triangular hole. And so the area is 18 by 18. Then you subtract off the hole, which is 1/2 of 9 times 9. And so that's the total area. And then the y bar is the sum of y tilde times area for the shapes, divided by the total area. But the whole 18 by 18, his centroid is at 0, so his y bar is 0. So this first term is 0. The second, the whole is a negative term. Its area is 40.5, and the centroid from him down to the x-axis is 2/3 of 9, which is 6. And so this guy's negative 6 times 40.5 here. If this hole happened to be below the x-axis, then the y bar would be negative, and the area would be negative. Okay? So be careful with your signs. The area could be negative if it's a hole, or if it's a cutout. And then the centroid of the shape, the x tilde or the y tilde, can be negative. If it's below the x-axis, the y tilde could be negative. Or if you're to the left of the y-axis, the x tilde could be negative. So that can happen. So that's that guy. And then here's a line. So here, like I told you, that occasionally you might see a line on a test. And so this is a line centroid, but you know how to do that now. Questions on that? Those are centroids. And so the integration could very well be conceptual, how to set up the integral. Composite area, I mean, I showed you an example with 4 different shapes, but the more common composite is just like 2 shapes, maybe something in a hole. And then finally, Pappus and Guldinus, you've got some choices on that. So.